Look out into the night sky and it feels like our universe is absolutely packed with galaxies in every single direction. There are stellar systems vastly larger than anything we could be ever expected. But here is the twist. Galaxies are not the largest structure in the universe. In fact, the biggest structure existent aren't made of stars, planets, or even gases. They are made of absolutely nothing and stretching across hundreds of millions of light years. This colossal expanse of empty space are true giant of our cosmos. We call them a cosmic void. Hello, I am David Banchari and welcome to my YouTube channel. In universe, the cosmic voids are the impulse, seemingly empty space that separate that a massive filament of the cosmic web. Will our voids look like absolutely nothings, but they aren't completely empty. They just actually contain a very low density of atom and just a scattering of isolated galaxies. For a long time, we didn't even know these cosmic voids existed, but in the late 1970s, a quiet revolution in astronomy occurred in two opposite sides of the globe. In 1978, American astronomer Stephen Gregory and Laird A. Thompson used the data from a Kitty Peak National Observatory to reveal in the distribution of the galaxies. But completely independently, at the exact same time, a stolen astronomer Michael Jover and John Anisto at the Tetro Observatory were presenting their own groundbreaking finding. They noticed identical waves to low density region, with Jover famously referring to them as a hole in a cosmos. Together, these independent discoveries fundamentally changes our understanding of universe in a large-scale structure. Just a few years after this initial discovery, in 1981, a scientist uncovered something even more mind-blowing. Astronomer Robert Krishna and his team, including Augustus Oemler and Paul L. Sector and Stephen A. Sackman, discovered that one of the largest cosmic voids ever recorded, often referred to as the Great Nothingness or the Wood's Void. This colossal expanse measures approximately 330 million light-years across. To put that in a perspective wave, our Milky Way galaxy were the size of a marble. The Great Nothingness would be bigger than a football stadium. But how exactly are these cosmic giants formed? The formation of cosmic voids is driven by several massive phenomena, things like primordial density fluctuation, baryon oxidic oscillation, and gravitational instability. Over billions of years, a matter naturally migrates from this empty space and pulling instant into a dense cosmic filament and galaxy clusters. Even today, the invisible hand of dark matter and dark energy to shape this vast expansion. To figure out how it all went down, we need to go back 13.8 billion years, right to the aftermath of the Big Bang. Right after the Big Bang, our universe looked nothing like it does today. There were no stars, no galaxies, and no planet. Instead, everything was a super hot and super dense slope of plasma, where matter slightly and a high energy particles slightly locked together. But did you know that during this cosmic infancy, the universe actually had its own sound wave? Because the early universe was so uniformly distributed and packed with a high energy plasma, it's actually allowed a sound wave to travel through a space. As the gravity tried to pull a matter together, its instant heat and light pushed it back out. This cosmic tug of war generated a massive acoustic wave or sound wave repelling through the early universe. Scientists call this baryon acoustic oscillation or BAO. But this sound wave couldn't travel forever as the universe expanded, its cooled down, and eventually it's become cool enough for the first true atom to form. When this happened, the light broke free and the sound wave abruptly stopped. But they didn't just disappear instant. Their final pattern were frozen directly into the fabric of space-time. This frozen wave created a primordial density fluctuation during period called cosmic inflection. At the subatomic level, space wasn't perfectly smooth because of quantum mechanical energy was constantly shifting. Some tiny spots were naturally a little bit denser and packed with just a friction more energy, while other spots were slightly emptier. Suddenly, inflation stretched the universe exponentially expand faster than the speed of light. It took over macroscopic subatomic bombs to instantly balloon them into a massive cosmic-sized ripples. Once the primordial density fluctuations were set in motion, a dark matter took over, actively shaping the massive cosmic web, and we easily see it today. But dark matter is different because it doesn't interact with light, it was completely impulsed to radiation pressure. While a normal matter was stuck and interact with light, but a dark matter was began acting like a universe's invisible scaffolding. In the region that started with a little extra matter, a dark matter quietly collapsed under its own gravity, building a massive gravitational trap. But in under dense region, there was barely any dark matter to begin with. This set the stage for an epic, loop-sided tug of war. Once the universe cooled down enough for regular matter to break free from radiation, it simply fall into a gravitational trap that dark matter already laid out. This triggered a runaway, a process known as gravitational instability. Gravitational instability is essentially a game of rich get richer and poor get poorer. Imagine a particle of gas sitting on the edge of under-dense region. Inside its own region, the gravitational pull is incredibly big because there is very little mass. But right next door, a massive ball of dark matter is extracting a powerful gravitational pull. What happened? The particle gets pulled out of the low density space and dragged into a high density filament. This is where the gravitational instability becomes a viscous cycle. As a matter fills the underdense region, that region loses mass. Because it loses mass, its internal gravity becomes even more weaker, and because its gravity is weaker, it loses the ability to hold on to anything else. Surrounding structure pulls a matter faster and faster. It's literally cosmic eviction. Over billions of years, this relentless training turned those minor repulses into the gaping of empty cosmic voids we see today. But voids are different. Voids are almost always shaped like a rough giant sphere. But the question is why? Think of it like a blowing balloon. When a matter evacuates, a void is emptied out of inside out. The expansion of voids is actually fastest along its shortest. Voids is naturally and actually fastest along its shortest axis because that's where the outside matter is closest and pulling the hardest. Because the slowest growing axis eventually catch up to the fastest one. Uneven expansion naturally smooth over a time. Voids act like an expanding balloon of dark energy pushing outward against the cosmic wave and shaping themselves in a near perfect sphere. Dark energy, roughly 68% of our universe, is made up of this invisible, smooth pressure of all space. discovered it in the late 1990s through the observation of the distinct supernova. Dark energy is the force responsible for accelerating the expansion of our universe. Unlike gravity, which wants to pull a matter together, dark energy acts like a cosmic repulsive force, pushing space itself apart. On one side, you have gravity, which wants to pull everything together. On the another side, you have a dark energy, a mysterious force built into the fabric of space-time that pushes everything apart. Now, in a dense region of space like galaxy clusters, gravity reigns supreme. They show a much mass and that their gravity completely overpower that suitable outward push of dark energy. But inside a cosmic void, there is virtually no matter, and because gravity requires a mass to function, the gravitational pull inside the void dropped to a near zero. With no gravity left to fight back, a dark energy becomes an absolute unchanged ruler of the emptiness. Because a dark energy has no competition inside the void, it doesn't just expand the space evenly, it accelerates it. As a dark energy stretches the space inside a void, it acts like an invisible hand pushing a whatever little metal remains towards the outer boundaries. But here is the kicker: as the matter fills to the edge, the voids become even more emptier. Less matter means even less gravity, which allows a dark energy to outward even faster. This aggressive expansion is exactly why astrophysicists are so obsessed with this void. They are essentially the ultimate dark energy thermometer. See, a dark energy is incredibly difficult to study because it's so subtle. But because voids are pristine pockets of pure space, free from a messy and chaotic physics of stars and exploding gas, they are just perfect laboratories to measure dark energy in its purest form. By looking at the distinct galaxies passes through this void, astronomers can observe how accelerated expansion stretches and distorts the shape of the void itself. By measuring the subtle distortion, scientists can calculate exactly how fast dark energy is pushing the universe apart. Voids taken the invisible makes to measurable the voids. For decades, the standard model of physics assumed that a dark energy was a cosmological constant. We thought it was a completely unchanging, the steady property of an empty space that would be eventually pushes the universe. But right now, a groundbreaking news data is telling that a theory is completely upside down. By mapping out of millions of galaxies, these massive cosmic voids deeper into space than ever before, the Global DISA collaboration, the Dark Energy Spectroscopy Instrument, noticed something bizarre. A dark energy might be actually be weakening over time. And a cosmologist didn't guess this. They caught it using a three independent line of evidence. First, baryon acoustic oscillation. These are ancient sound waves frozen into the fabric of the space-time, acting as a cosmic yardstick. But measuring how the frozen wave grow inside or around the cosmic voids across 11 billions of years, scientists realized that our modern universe isn't expanding as fast as it should be. Second, type 1a supernovae. This exploding star always denoted with the exact same brightness, acting as a cosmic candle. When we measure their distance against the much their light has been stretched, the history books show as a subtle slowdown. And third, the equation of state or W. In Einstein math, this value must be equal to rock solid -1 if dark energy constant. But the combined data show W is dynamic. It actually look like a dark energy density packed about 4.5 billion years ago and has been steadily declining ever since. Let add that a sink in the dark energy is running out of the gas It's completely rewrite the ultimate fate of our cosmos. Stand of a blank, depressing future where every galaxy drifts so far apart that the night sky goes completely blank. But a weakening dark energy open up. A dark energy is actually something called quietnesses, an evolving field. It continues to decay. Expansion of space might be eventually stabilized or gravity could take a wheel once again, pulling that universe back together in the cosmic race. It is wild to think that the empty space we once ignored are actually the key understanding of ultimate fate of universe. With a gravity working tirelessly to build the structure of the cosmos, a dark energy is busy to carving out the massive voids in between. The next time you look up at the night sky, remember the empty space out there isn't just a nothingness, it's a dynamic force of shaping the future of the reality.